All right, in this section, we're going to go a little bit farther with the chi-squared testing. And this time we're going to be looking at two variables to see if they're related to one another. So let's write down some definitions. Two events are independent if neither one impacts the probability of the other occurring. So, for example, tossing a coin. Each time you flip the coin, it doesn't matter what happened on the previous flips or the next flips. They're independent of each other. So the flips do not flip, number 5 does not affect flip number 8, or the probability of number 8 occurring. Tossing a coin, throwing die. So these are examples of independent events. And a lot of times we're not absolutely certain if events are dependent or independent until we analyze them. It's not always evident right off the bat if something is independent, like these things that I've thrown down here. So it's not always easy to determine when events are independent. In fact, we're going to be looking at situations, we're going to be trying to see if two variables are independent. So like an x and a y variable, and each of those would have its own sequence of events or whatever events they would define. And these are either completely independent or they have some dependencies. As an example of what I mean. For example, does your consumption of fatty foods increase your risk of, say, diabetes? Now we know sugar foods and things like that will have an effect. What about fatty foods? Not absolutely certain. What about ice cream? These are the kinds of studies that you see in newspapers all the time, trying to determine if there are links between certain modes of behavior and certain diseases that you might get. Let me start with a definition. An R by C contingency table shows the observed frequencies for two variables. We'll use R rows and C columns. Let's use an example to motivate what this section is all about. Suppose we survey coffee drinkers to determine their preference. So we give them a list. Let's say they look like this. Here's my options. I can look at just plain black coffee. That would be certainly one thing to consider. And then just black with sugar, cream only, cream and sugar, and then the catch-all for anything we haven't thought of, other. The survey was presented to 3,093 coffee drinkers and the results are as follows. So this was broken down between male and females. So there's one variable right there. Gender is a variable. You could possibly give it numerical values by saying that males were worth, say, 1 and females were worth 0, or vice versa. It really doesn't matter. And then we have our plain black coffee. We have our black with sugar. We have cream only. We have cream and sugar. And then other. And here were our numbers. For plain black, we had 103 males, 78 females. For black and sugar, 300 males, 189 females. Cream only, 24 males, 65 females. Cream and sugar, 1,000 males, 957 females. And for the other category, 213 and 164. Now this table has 2 rows and 5 columns. So we'll create a 2x5 contingency table. Now, assuming the 2 variables, what are they? Gender, there's one variable, and coffee preference. So if we make the assumption that the 2 variables are completely independent, then the percentages of males who like a particular type of coffee should be the same for females. Let me put it in words a little better. Suppose, for example, we looked at people's preferences for one of these coffees, and let's pick one. Let's just say plain black, for example. If the gender were independent of the coffee preference, then it would mean that males and females would choose any of these categories of coffee in the same manner, in the same percentages. So if 10% of males like their coffee plain and black, then if these were completely independent, then 10% of females would also happen to like their coffee black. So we wouldn't be able to tell the difference between male or females in this scenario. All right, now what we're going to do is create a list of expected values from the ones that we have. So we're going to measure the expected frequencies. Well, let's just say the frequency of a cell. And this is where I make this notation, E sub R comma C. So we're going to be talking about row R, column C, and the formula looks like this. We're going to take the sum of row R, multiply it by the sum of column C, and then we are going to divide it by the sample size. So in our previous one, what we're going to do is do these computations for all of them. Let me come back to the table for a minute. The way this table works is this way. Males, all across males, that is the male row, or row 1. The female row is row 2. And then we have 4 columns, or 5 columns. This first column, second column, third column, fourth column, and then, of course, the 5th column. So I need to get an expected frequency for all 5 across and 2 down, so a total of 10 different spots. So let's see how we create these things. Let's start with E 1, 1. So I'm going to go across row 1, the sum of row 1, times the sum of column 1, and I'm going to divide by the sample size. Before I can do this, then, I need to get the sum of row 1 and the sum of column 1. In fact, I need to get the sum of all the rows and the columns. So I'm going to grab our table so it's around, and we'll go from there. So let me add up every single column and then every single row. Some of these are pretty easy, so I'll just go ahead and do them. 181, 489, 89, 1,957, and 377. Across the rows, I've got 1640 for my first row, and I've got 1453 for my second row. And if you recall, the sample size was 3,093. So if you check all of these, notice that 3093 is the sum of these two entries in its column, but it's also the sum of all 5 of these items going across its row. So it adds up the same for both. Now let's do E11 again. E11, I want to go the sum, so and 103 is what I'm looking at. If I look across that row, the sum of that row is 1640, and the sum of its column is 181, and divided by the sample size. And then E1 comma 2, now I'm in position where this 300 is. I'm in row 1, but I'm in column 2. So if I look across at row 1, 1640 is the sum across that row. But the sum down the second column is 489. Let me continue. So as long as I'm in row 1, I'm always going to have something like this. And I'm going to keep being in row 1 as long as I don't get as long as I don't go past the 5th column. Now, let's take a look at this 3. Represents the 3rd column. The sum of the 3rd column is 89. This 4 is the 4th column. That's 1957. And then over here, I want the 5th column. That's 377. Go ahead. I think I'll probably go to 4 decimal places for each of these. So let me go ahead and get these to 4 decimal places. That one I'll have to sneak in there. And let's pull up the calculator for this purpose. If you're in any kind of a screen, get out of it by quitting it. And let me go ahead and get my numbers. About 95.9715. 1640 times 489 divided by 3093, 259.2823. Now, when you finished row 1, that's where the 1 came first. Now I'm going to move on to the female row, which is row 2. So for row 2, all of the sums of row 2 is 1453. Everything else will pretty much be the same. And let's go ahead and find these column numbers that I've left blank. So the first column was 181. Second column was 489. Third column was 89. Fourth column was 1957. And the fifth column was 377. And let's go ahead and get these numbers in. Now, what would be a good idea to do is to recreate the table, but to put these values right with it. So let me go ahead and get my genders. So we have male, and I'll give myself space, female, and then totals. And then we had plain black coffee. Then we had black with sugar. Then we had cream only. Then we had cream and sugar. Then we had an other. And let me put in my numbers. 103 is what was in there. For this part, I'm going to put underneath of it, in the 1-1 spot, I have the 95.9715. That's the expected frequency. I know it's a decimal and everything like that, but mathematically, this is the expected frequency. And then when I put the 78 underneath of that, I'll put my 85.0285. So look for E21 for that one. And then I'll just go in and put in the rest of my numbers that I was given. And let me put in the expected numbers. Now that I think about it, I don't need totals for this. I have everything that I need. What I'm going to do now is put these into the calculator, and the way I put them in, I'm just going to go, the order really doesn't matter how you put them in, as long as when I put an observed amount like the 103 and the expected right next to it, I put the 95 there with it. So let's go and get the calculator and open up your statistics menu. And let's edit. And whatever you have in there, just start deleting your way out of it, so it's no longer there anymore. And let's go ahead and overwrite. So like I said, the order is really not important how you do it. I don't know if I can get myself. Oh, here we go. I think that'll work. Let me go and get these numbers. I am going to go first row, and then I'm going to go second row. So once you got those, it's not a bad idea to go through and make sure that you had them all right. Notice that the column, when it displays in the column, it will round to fewer decimal places usually than when you put. But once you highlight them like I'm doing here, you can see that it's keeping all the decimal places in, so you don't have to worry about it rounding on you. All right, now that I've got that, I want to take a look at these expecteds and make sure that each and every one of those is at least 5. You see, this is no different than what we did last time. It's just the degrees of freedom are calculated a little bit differently, but everything else is exactly the same. They're still going to use the chi-squared goodness of fit test for this. Now let's take a look at my hypothesis statements. H naught would look like this. The variables gender, and coffee preference are independent. And then HA would be the variables gender and coffee preference are dependent. The degrees of freedom look like this. You take R minus 1 times C minus 1. So the number of rows minus 1. So we had 2 minus 1 times, and then we had 5 minus 1. We had 2 rows, 5 columns. This is 1 times 4. So this is equal to 4. And so to invoke what we want, we are going to go to the Stat menu. That, of course, is the Stat button. And then we are going to go to Tests, just like I did last time. After that, we're going to choose Test D. That's the chi-squared goodness of fit test. So let's go ahead and do that stuff. Stat, Tests, scroll all the way to the bottom, or, well, you've seen enough of this by now. Go to number D, or letter D, hit enter. I've put my observed in L1 and I've put my expected into L2 just like we want. The degrees of freedom, though, is 4. And now we're ready to calculate. So I see I got my chi-squared and I got my p-value. Let me write those things down. So my test stat, that's the one that looks like this. O minus E squared over E. Well, the calculator gave them to me. Let's see what I got for it. That's 43.704. And then the p-value, 7.39 times 10 to the negative 9th. By now, you know what that means. That means that it's actually equal to 0. And I'll have 8 zeros before I get to the 739. Now, if alpha were to equal 0.01, we could see that P would be less than alpha, which would mean that we would reject H naught. And we would conclude, that there was some dependency on these things. They were not completely independent. Now, if instead you decided to use the classical method, what are we going to use? Well, the same. Alpha is 0.01. The degrees of freedom will still be 4. And then we'll pull up the chi-square table. Let me increase its size a little bit. So the degrees of freedom is 4. And go down to alpha equals 0.01. I get 13.277. And so when we draw a picture of this, remember the chi-squared distribution is not symmetric. So my chi-naught squared, that's the 13.277. And if I look at my test stat, you can see it is way buried into the critical region. We see that we would reject H naught. So I would conclude that these variables are not independent. Let me clue you in about something and why the test is the way it is. I want to come back to my table of values that I had before. Now, I've brought these back up. Check this out. If you take this 95.9715, and you divide it by its row, which, if I'm not mistaken, the totals at the end, we had 1640 for the male row and 1453 for the female row. If I take the male expected number here and I divide it by the 1640, look what I get. Here, if you look, it's about 0.585. Let me do the same thing for the female one. Let me take the parentheses amount and divide by its row. Now, there's some rounding and whatnot, but you'll see we get the same number, 0.585. Or if you want 5.85%, 5.85%. If the choice of coffee were independent of gender, then we would expect the percentage of females who enjoyed black coffee to be precisely the same as the percentage of males who enjoyed black coffee if this were completely independent of gender. And I can go around and do the same for each and every one of these other values in parentheses, and I'll get the same percentage here as I would here, same percentage here as I would here. And then you can do a column version too to show that the coffees are independent of gender as well. So that's why the expecteds are, when you put those in there, those are acting like there is absolutely no dependency whatsoever, complete independence. That's what the expected numbers are telling us. And so the survey numbers, when we plug those in and then we compute all those computations, we are computing how far away from complete independence our data is. Let's do some more examples. For this next example, I want to perform a chi-squared goodness of fit test for the following. Data, and we will use alpha equals 0.05. So what we have here is we have the results of some medical treatment. So the patient either experienced nausea or no nausea. And it depends on what they took, the drug or a placebo. And let me put down the numbers that we have. And then while I'm here, let me put my totals up also. So remember, to go across, I'm going to add up the 36 and the 49. Actually, I made a mistake there. That's 13. 36 and 13 is 49. And then 254 and 262 is 516. And then let me get the totals of the columns as well. The total of the first column is 290. The total of the second column is 275. And then the third column, the total is 565. Now, remember, what I want to do is put what we expect to have for these. 565 people were involved in this test, or were involved in this process. So we have 565 patients, and these are what happened depending on if they took the drug or a placebo. Let me go and get each of the expected information. I'll put it underneath of here. So if you remember, in this spot right here, that's called E11. And that's where you sum of row 1 times sum of column 1. And you divide that by the sample size. Let me put in my information. The sum of row 1 is 49. The sum of column 1 is 290. And the sample size is 565. 49 times 290 divided by 565. I'll go 4 decimal places, so I have 25.1504. So my next position here, I'm still in row 1, but I'm in column 2. So let me do E1, comma 2. So that's the sum of row 1 times the sum of column 2. All of that is divided by the sample size. So row 1 had 49. Column 2 has 275. And then we have 565 for the sample size. To 4 decimal places, I've got 23.8496. So let me put it into this spot as well. 23.8946. And then I'll move on to the second row. I'll start with, it looks like I didn't give myself space in here to put these things in parentheses. So let me put the totals underneath of that. That was still 290. This was still 275. And this one was 565. All right, so E2, 1, that's the sum of row 2 times the sum of column 1 divided by the sample size. And row 2, if I look across row 2, I have 516 for that total. Column 1 was 290. And of course, 565 is our sample size. Uh, 264.8496. And that goes into this spot. And then finally, this last one, which will be in E22. So that's the sum of row 2 times the sum of column 2. And all of that is divided by the sample size. So what do we have for that? The sum of row 2 is 516. Column 2 is 275 over 565. $251.1504. So let me put that in here. 251.1504. Now remember, the first thing we're supposed to check in all of these is to make sure each of these numbers in parentheses is greater than or equal to 5. We're good. So we have that down. Now let's get our H0 and HA. So here we'll write for H0 the variables. And here you might need to look and see what these variables are called. Let's come back up to my table. So I have variables being result, and the other variable, I think let's call this treatment. All right, so I've got my results here, so result versus treatment. The variables results and treatment are independent. And then for HA, the variables results and treatment are dependent. So now that we have our information, or we actually have our information, then all I need right now is to simply put these into the calculator. So let's pop into there. Let me move myself out of the way. So we're going to have a total of, I have 4 observed values, and then I have 4 expected values. So let's go into Stat, Edit, it's already on that, and then start deleting everything that is in there. We had more data before than we do now. This is a smaller problem. And let me go ahead and put in our numbers. And then make sure you put in, so across from 36, make sure you put the 25.1504. And then once you got them all in, I do recommend you go through and just make sure that you entered the right data, because there's a lot of steps to these problems, and it would be crushing to get to the rest of the problem, or to get finished with the problem and then find out that you put in a wrong piece of data somewhere. If you're going to use the calculator for everything, all you have to do is put in the data correctly. That's the extent of what you need to do. Let me give myself some room on the page. And let me go ahead, if you'll remember, in the calculator, get out of here. It's a good idea to quit this. Go to Stat, Tests, and then scroll down until you see D, chi-squared GOF test. And all you have to do is enter. Now, as we normally have, we have the observed is in L1. That's what I'm always been doing. And the expected is in L2. However, the degrees of freedom, the contingency table, was 2 by 2. 2 rows by 2 columns. Remember, for the degrees of freedom, you're going to take the number of rows minus 1 times the number of columns minus 1. So we're going to have 2 minus 1 times 2 minus 1, and that's just 1 times 1, 1. So let me go ahead and put in my degrees of freedom equal to 1 and see what we have. I get chi-squared 10.564. Remember, this is the test stat. And it also gives you the p-value. For that, I have 0.001. I'm just going to go to 3 places for this. Now, for this problem, I think the alpha was 0.05, but let's scroll up to the original state. Yes, alpha was 0.05. So I'll put it underneath it there. Well, it's quite clear that P is a lot smaller than alpha. P is smaller than alpha, so we reject H naught. If, on the other hand, you want to use the classical method, we need our alpha and our degrees of freedom. And let's go ahead and use the chi-squared table to get me my chi-naught squared. So the degrees of freedom is the very first row, and we're going to go to alpha equals 0.05. So I have 3.841. So chi-naught squared is 3.841. So if you recall, we get a picture that looks like this. And the test stat was given as part of our GOF test. And you can see it's way off to the right. So even the classical method, of course, says reject H naught. All right, the last example I have here, I want to try to do this, but in a way that uses the least amount of effort as possible. So I'm not going to bother making up my own table here. I'm going to put in the totals right on this table itself and the totals down here as well. And let me get this information here. I have 399. I have 142, 82, 970. And then for the row totals, I have 504, 728, and 361 for a grand total of 1,593 people. And let me make sure that I know which row and everything these are up to. So now what I'm going to do is plug this information into my calculator. So let me get the observed. I have a total of 3 by 4, so I have 12 pieces of data to enter. So let me grab my calculator. I'll move it out of the way. Now I only had, I think last time, 4 pieces of data in my stat, so I can just overwrite it with more data. So the way I'm going to do it is I'm going to go across, I'm going to do all row 1, then I'm going to do all row 2, and then all row 3. All right, so I've got my observed in. Now, for the expecteds, look what you can do. You can actually, let me get to the top of the list here. I'm going to overwrite these things, so I want to get to my first one. What you can actually do is this. Remember, if I want the expected for this first spot, I need to take this row total, multiply it by this column total, and then divide by 1593. Well, if you want, see, here's what I can do. Let me do the row total first, the 504. You can actually type it in. So I can go 504 times 399 divided by 1593, and it'll do it all for you. You see that it puts the total in there. That's really not what I care about anyways. I just care, well, the total is what I care about, but as long as it gets the data in that spot, that's all I care about. So let me move to the next piece where it's got this 34. So the row is still 504, but now the column is 142. So I'll do 504 times 142 divided by 1593 and hit enter. And then that's how I'm going to do all 12 of these. So next I'll move to the 10. And then I'll move to the 311. So I have the 504,970. And then I'll just continue on. Next, I'll do row 2, and then I'll do row 3. Once you have your data entered, go to, well, I recommend quitting this. Go to just stat, tests, look for test number D, L1, L2. The degrees of freedom, here our table is 3 by 4. So our degrees of freedom, we have 3 rows by 4 columns. That will be 3 minus 1 times 4 minus 1. That'll be 2 times 3, which is equal to 6. Chi-squared is 38.746. And the p-value, let's get that one too while we're at it. P is 8.026 times 10 to the negative 7. And you know how to deal with that by now. So if I just wanted to use the p-value method, remember this is 0.1234567 8. Alpha equals 0.01. So P is less than alpha, so we reject H naught. We reject H naught. If we want to use the classical method, we have our alpha equals 0.01, and our degrees of freedom was equal to 6. Our chi-squared test stat was 38.746. There's our test stat. And let's just go ahead and get what chi-naught squared is. Use the table. So the degrees of freedom is 6. Alpha is 0.01. 6. 16.812. So we draw a picture of the situation. Here we have 16.812 as our cutoff. And right here, the test stat is way, way out there. So we reject H naught.